Good morning, everyone. How are you doing? Confirm that you can hear me. Okay, great. Thank you. I hope you enjoyed your weekend. Okay, I think we can start now. So good morning, everyone. Welcome to our last section on complex numbers. And we will finish off tomorrow on complex numbers, but this is the last section. And so we are going to talk about roots of complex numbers. But before we get into that, I thought maybe I should talk about the principle of mathematical induction. Someone asked on Discord how to use principle of mathematical induction. So we used it. So this is principle of mathematical induction. And we used it to prove part of De Moivre's theorem, if you remember, on Friday. So we used it. So we used it for this, right? To prove this. But basically, maybe let me just talk about a bit of what it entails. So, number one, it is used to prove statements that are true about natural numbers. So, so if you've got a statement about natural numbers, so this simply means that the statement involves some natural numbers, and it has to be true for every natural number, right? So it's about natural numbers, and it's true for every natural number. So basically, the statement will go as something, and then it says this for every n natural number. You can include 0, it's still fine, because it will still work. You just need to check for n is equal to 0, right? So it will be a statement, something about which involves this n somewhere, and you are saying this is true for any natural number. So if you think of De Moivre's theorem, then you see also that it has some n in it. Yeah, even though it's for integers, we can restrict it to natural numbers for part of the theorem. And then the second part, we just need to look at negative natural numbers. Not negative natural numbers, but negative integers, right? So it will be a statement for every n natural number, right? So the way we prove, or the way we use mathematical induction to prove this type of statements is to start off. So the first step is what is called the basis step, or base step, right? So basically here, what you want to do is to prove that whatever statement you have, which involves and this n is true for n is equal to 1. So this is like the general case. Sometimes you might have a statement that starts at maybe n greater or equal to 4, for example, where n is a natural number. So you're saying for all n that are for all natural numbers that are greater than or equal to 4, this is true. So your step or base step will change to wherever you're starting at. So if it's just natural numbers, you start at n is equal to 1. But if, for example, it has this type of restriction, then you start at n is equal to 4. That would be your basis step for this part, right? But basically, the first natural number that you want to check is what you want to show that, well, the statement is true for that n is equal to 1. If you see that sometimes in statements, this is easy because either it's something that is obvious or maybe you have already assumed that it's true in this basis step. And then the second step is the induction step. So here there are two parts to this step. So number one, you have to assume that the statement is true. So it is true for n is equal to k for some fixed natural number k, right? And sometimes this particular step, this first step here is called the inductive assumption. So you have to assume that this statement is true for some k, for n is equal to k, where k is some fixed natural number. And then the second part is to then prove that the statement is true for n is equal to k plus 1, right? And then you have proved that it is true for any natural number. So basically what it says is just maybe a bit of logic of how it works. So there's a question which I think I'm going to answer just now. Chris says, we are using an assumption to prove that something is true. Why are we allowed to do this? Okay, so let's see how it works. So suppose we've got a statement and we have shown that it's true for n is equal to 1, right? So we know for n is equal to 1, it is true, right? So here, this step, if you look at this step, what it actually is saying, it is saying, assume that it is true for n is equal to k, right? And then you prove that it is true for n is equal to k plus 1. So what this second step is saying is, if it's true for n is equal to k, then it's going to be true for n is equal to k plus 1, because we would have said, we assume here, and then we show this happens. So if it's true for n is equal to k, it's going to be true for n is equal to k plus 1. So for example, we know from the basis step that it is true for n is equal to 1, right? So this second step here is telling us that because we know it's true for n is equal to 1, that deals with this assumption, right? This assumption is just saying, maybe let me write the inductive step in a different way. If true for n is equal to k, then true for n is equal to k plus 1. That's what the statement is really saying, right? If it's true for n is equal to k, it's true for n is equal to k plus 1. From the first part, we have proved that it's true for n is equal to 1. So what it means is, if it's true for n is equal to 1, we know that is true for n is equal to 1 because of the basis step. Then it means by this second step, it's going to be true, then true for n is equal to 2, right? Because we know it's true for n is equal to 1. So the inductive step, when we do it, we have shown that this happens, right? If we look at now, we can move on to say, so because it's true for n is equal to 1, it's true for n is equal to 2. So now we can assume that is true for n is equal to 2 because, again, we know it's true. And then we use this step again, this inductive step, which tells us if true for n is equal to 2, n is equal to 2, then it is going to be true for n is equal to 3, right? So you can see that we can continue until we cover all the natural numbers that we have, basically. I think that's the idea there. I don't know if that is clear. Let me see the comment. So then if we make k is equal to 1, then it will be true for everything because you just keep taking, yes, 1 plus 1 plus 1 for all natural numbers. Yes, so that's the idea there, that once we know that it's true for the first one, and then we have shown that if it's true for 1, it's true for the next consecutive number, then we can then say it's true for 1, so it's true for 2, it's true for 2, so it's true for 3, until we finish all the natural numbers. That's the idea behind the principle of mathematical induction. Right. So I hope that clears that. If you want, in Appendix A2, just to see how it works in general, because there are a lot of examples there and a lot of questions that you can sort of look at to see how the principle of mathematical induction works. So you can go to this at the back of the book, Appendix A2, and see, you can read what I've just explained here, and then you can also see some examples and some exercises. Right. So this is a very powerful tool that if you're continuing with math, you will probably use over and over. So it's good to master it now, so that whenever you need to use it, you're already familiar with it. Okay, so that is that for principle of mathematical induction. Let's get into the work that we want to look at. So again, we start off with our definition. So we've got the standard form of a complex number, which is z is equal to x plus yi or iy, whichever you prefer. I don't think there's a problem there. And then polar form, z is equal to r cos theta plus sine theta I. Sometimes putting I at there sort of as a problem if you've got something like sine there, but it's not a problem. I think as long as you know what you're writing, it's okay. And then we have got the shorthand, which is r e to the theta I, like that, right? And then we also talked about principal argument. And we said our principal argument is between minus pi and pi. So this is a closed interval, like that. Right, and then we proved, well, part of de Moivre's theorem, and I think you can do the other part as an exercise. It should be, I'm not sure if it's in the homework or it's part of the exercises anyway. Right, so we've got, if you've got a complex number written in polar form, plus I, maybe let me be consistent for once in one lecture. So sine theta I, and you've got, this is an integer, then z to the n is equal to r to the n cos n theta plus sine n theta I, like that, right? Which we can write in the other polar form shorthand, which is e to the n theta I. And then we've got De Moivre's theorem there, right? So now we go on to chapter 6.5, which is on roots of complex numbers. So you can see this, you'll see that this theorem sort of comes in handy when we are dealing with roots of complex numbers. So let's start off with a definition. So this is section 6.5, which is roots of complex numbers. All right. So let's see. So let Z be a complex number and N be a positive integer. Right? So we are talking of a natural number here. Then what we call an nth root of the complex number Z is a complex number. Let me write, is a complex number W such that W to the N is going to be equal to the complex number Z. So if you try to think about it in terms of numbers already, so if you say the square root of 4 means that if we say 2 times 2 to the 2 is going to be equal to 4, right? So basically nth root means if you multiply W n times, if you multiply W by itself n times, then you're going to get Z, right? And so we want to be able to find nth roots of a complex number, basically. So we've got an example in the textbook, and it is example 6.5.2. It says, let Z be the complex number I, and then show that W, which is the root of 3 over 2 plus half I, is a cube root, right? So it's just saying cube means if you're thinking in terms of this, we are saying the third root, right? Cube root of Z, right? So we are given the W, and then we want to check if it is indeed a cube root of that. So the first thing would be to say, well, to make our life easier, we can just write our our W in polar form, right? So if you draw a little diagram there, you've got half there, and then you've got some number which is root 3 over 2. So you're somewhere there. So we can see that our argument there is in the first quadrant, basically, right? So we can say what is the modulus of Z? It is going to be equal to the square root of root 3 over 2 squared plus half squared, like that, and that is going to be equal to root 3 over 4 sorry, not root 3, the square root of 3 over 4 plus 1 over 4, which is equal to 4 over 4, which is 1, right? So the square root of 1 is 1. So we know that the modulus of that is 1. And then to find the argument, then you say 1 cos theta plus I sine theta is equal to root 3 over 2 plus half I. And then maybe let me put, so that I'm consistent throughout, let me put my I there. And then, so what it means is, if I take the real part on both sides, it means cos theta is equal to root 3 over 2. And then this tells me that theta is going to be equal to pi over 6. Or what's the other angle? So if I draw my little diagram there, all STC, then I'm saying this is positive in here and in here. So, or minus pi over 6. So these are the two cases that cos is positive. And then if I then take the imaginary part and say sine theta is equal to half, then I can see that it has to be positive. So sine is positive. Let me put a box in there and in there, right? So the common one is this one. So therefore, and this is pi over 6. Therefore, theta has to be pi over 6. That's why it's both positive in for cos and sine. That's right. And again, I told you a little hint here that if you look at your complex number, right, the sign of the imaginary part should be the same as the sign of the one on the angle that you're going to end up with, or the argument that you're going to end up with, right? So we've got pi over 6. So in other words, W can be written as 1 times e to the pi over 6i in polar form. So this is that in polar form. And once we get that, then we can check. So what it means is we are expecting to say W to the power 3. And then once we get that, we want to find out that W to the power 3 is going to be equal to the complex number I. Right. And what happens? So we say W to the power 3 is going to be equal to 1 to the power 3 times E pi over 6I to the power 3, which is just e to the power over 2I, right? If you multiply there, you get pi over 2I, which is equal to I, if you think about the complex number. So this complex number is modulus 1, right? And then if you look at the argument here is pi over 2, so pi over 2 would be somewhere here. So the modulus is 1, so we expect it to be here, so it will be 1I, or just I. So this would be our complex number there, right? So we get that. And there's a question, can we find the argument by computing arctan of that? Yes, so you can also do that. That is perfectly fine. So there are different ways of finding your argument. You can use whichever works for you. But yes, that one works, because if you say the tan of, if you draw a little triangle here, you can see that this is root 3 over 2, and then this is half. And then because we want this angle, we can say opposite over adjacent, so half over root 3. So tan theta would be equal to half, which is the opposite over that. So you can use that. That's another way. You just need to make sure that you get the sign right. Sometimes you might not get the sign right if you just use this. But if you have drawn the the triangle, you will know which quadrant the complex number is in, or at least the theta, which quadrant it is in. So therefore, you'll be able to figure out what is the appropriate sign for the angle, for the argument. Right. Okay, so we now know that this is true. Now the question that comes is, okay, so we found out that this complex number is actually a cube root of z. So the question is, that should follow immediately is, are there more cube roots of I? So we know one works, which we were given. Are they more? And the next question is, how many if there are more? So maybe we can say if more, then how many? How many more, right? And this is the, we want to answer this question. Maybe even we'll get to the end of the lecture, trying to get a proof of how to answer this question, or these questions that we have, right? But before we do that, we've got a theorem which is 6.5.3 in the textbook, and it says, consider two non-zero complex numbers, z, which is equal to r1 e to the theta 1 I, and w, which is r2 e to the theta 2 I, right? Then we've got, so when we are in polar form, we've got different ways of expressing our complex numbers. So therefore, we need a statement that tells us about equality of complex numbers when they are in polar form. When they are in standard form, we know that we want the real parts to be the same and the imaginary parts to be the same. But when they are in polar form, you will notice that there are different ways that you can express the same complex number. And so we want to know what equality means when we are dealing with complex numbers in polar form. So we say z is equal to w if and only if the moduli of these two complex numbers is the same. That's fine. But on the angle, we have this theta 1 is going to be equal to theta 2 plus 2 pi k for some integer k. So we can see that for the angle, because we know that sine and cos are periodic with 2 pi period. So whenever you add this, it's not going to affect the actual angle when you're trying to find cos or sine, right? So therefore, we've got this that tells us that when we say two complex numbers are equal and they're in polar form, their moduli should be the same, but the angles, you can say theta 1 is equal to theta 2 plus 2 pi k, where k is some integer. So if you add a multiple of the of 2 pi, then you still have the same angle, right? If you're talking of the argument, then maybe you've got you are restricted. But if you're just talking about the principal argument, then you've got restrictions. But if you're just talking about any argument, then you're going to have an infinitely you're going to have infinitely many of these angles or arguments, right? Right, and for the proof, so we are not going to do the proof. You can look at it in, I think it's in the textbook. But the two things to note is this if and only if here, right? So we are saying Z is equal to W if and only if this happens. So for the proof, we want to prove two statements, because whenever you see if and only if, it means you've got two statements. One of the statements is, so if you're going in that direction, what it means is if Z is equal to W, then R1 is equal to R2, and theta 1 is equal to theta 2 plus 2 pi k for some integer k. For some integer k, right? And just waving my hands here, if Z is equal to W, we know that the moduli have to be the same. Otherwise, we have problems. And then, as we have explained, if you add a multiple of 2 pi to any angle, you still have the same cos and the same sine. So therefore, we would expect to have the same complex number. And then going in that direction, I think it's an exercise. But the statement that you want to prove is if R1 is equal to R2 and theta 1 is equal to theta 2 plus 2 pi k for some integer k, then it means that the two complex numbers are equal, right? And this is exercise 6.5, number 6 in the textbook. So you can go and have a look. So there is a comment or a question or questions. Is there a possibility of not getting a common angle for cos and sine? If yes, then how would we conclude about its polar form? I don't know what you mean by a common angle for cos and sine. Maybe elaborate on that, what you want to say. But if I think I got the question, if you are between, for example, minus pi and pi, then you're going to get a unique argument or a unique angle that is going to work for cos and sine. And if you are between 0 and 2 pi, it's the same thing. You're going to only get, if you think about the graphs, they look like, I think this is sine. So if you move from 0 to 2 pi, you can see that there is no point that you can sort of pick. Is this correct? Maybe not. This, okay, let me see what is the graph of sine, just to be sure what I'm talking about. Okay, so what are we saying? Okay. So okay, so if we had okay, so what I wanted to say was, okay, so we can see that we can get two values for cos, right? But if we draw the other graph, which is the, I think it looks like that, you would see that for my graphs are not nice. Okay, you would see that for cos and sine, so for a particular cos and sine, you're not going to get the same the same value. So I was saying, if you take, for example, this point there, if we go down there, you see that for these angles, we are going to get the same value. But if you think about its cos, it's going to have a different value, right? For the same, if you look at the two angles, this one will be somewhere there, and then this value will be somewhere there, right? So that then differentiates for any angle, you're going to get unique theta such that which is going to cater for cos and sine. I'm not sure if that is clear there, or if I'm even answering the question that you wanted to ask. But the theta is always unique when you're dealing with this type of cases in general, right? Just like what we were doing when we were looking at this, there's only one theta that is going to satisfy all the conditions that we have. So cos and sine in this case. If you go to any complex number, that is the case. If you still want to, if it's not clear, let me know so that maybe I can elaborate, or maybe you can rephrase your question so that it's a bit clearer. Right, so I was talking about this theorem that tells us that if you have got two complex numbers that are expressed in polar form, then you've got that the moduli is the same, but the angles can be different, but they only differ by a multiple of 2 pi. That's what it's really saying. All right, okay. So you say I understand what you're saying. All right, okay. Basically, we've got a unique theta that is going to work. Right. So that is the theorem there. And now we get into, I think, the main theorem of this section, and that is theorem 6.5.4, and it is answering these questions here. And it says, let Z be equal to Ri theta I, sorry, R e to the theta I be a non-zero complex number, non-zero complex number, and theta, so with theta being the principal argument, so we are restricted between minus pi and pi, principal argument of Z, then for every positive integer, n, Z, the complex number Z has exactly n distinct nth roots. W not W1 up to the last one, which is Wn minus 1, which is given by Wk is going to be equal to the nth root of R, right, of the real number there, times e to the theta plus 2 pi k over n, so that's a number there, I, where k ranges from 0, 1, up to n minus 1. So we answer the question, are there more? Yes, there are. And how many are they? They are going to be exactly 3. If you want to find the cube roots of I, they're going to be exactly 3. If you wanted to find the square root of I, then you're going to have 2. If you want to find the fourth roots of I, then you're going to have exactly 4. And they're given by this formula, right? So something to note is, number one, the complex number that you are dealing with is such that the theta, when you write it in polar form, the theta is the principal argument, number one. Number two, you know that if you are given any n, you are going to get exactly n distinct roots. So the number is exactly n, and they are also distinct, right? So one is not equal to the other roots that you're going to get. And the formula is that. So we can see there n because we started w naught and we end up at wn minus 1, right? And so the wk here is connected to the k from 0 to n minus 1, and the k is also there. The n here is a fixed one because we are saying for every positive integer. So for a fixed n, we can get all these roots of that complex number. Right, so we are going to do the proof of this. I don't know how far we'll go. Maybe we will just look at some part of the proof. Okay, so but basically we need to understand what the proof is about. So we need to prove that there is exactly n distinct roots and all of them are of this form, right? So let's see what we have. So step one that we have, so we've got 3 steps in this proof. Step one is to prove that wk is an nth root, nth root of z for every k which is between 0 and n minus 1, right? Right. So basically what we are trying to say is all of them work. The ones that we are given work. So if you find wk to the n, you should be able to get z. That's the first thing, right? Just checking using the definition. If you remember what we did in this question, where we had to show that this complex number is a cube root of z. We just had to find, to say w to the 3, and then we see that it's going to give us I. So that's the first step. We want to check for all the complex numbers that we are given in this proof or in this formula. All of them are complex numbers. They are nth roots of z. That's the first step. And then the second step is, because here we are saying exactly n, it means that if I find anything else, if w is an nth root of z, then w, which is wk, then it's going to be one of these, basically, right? Because we want them to be exactly n of them, and if we show that all of the n that we have are nth roots of this, then if I find any other root of z, we have to show that it is one of these that we already have, right? Because we want them to be exact. And then the last step is the distinct part. We are saying that all of these complex numbers that we have are distinct roots. So in other words, if I take P and Q, which are an element of this set, if P is not equal to Q, so in other words, because if P is not equal to Q, it means I'm taking WP and WQ, where P and Q are not equal, then it should mean that WP should not be equal to WQ. Then I know that indeed all the complex numbers that I have are distinct. That's what the step 3 means. Then if we look at all these, then we have shown that indeed the statement is true. We have dealt with the fact that there are n of them. Well, we've dealt with the n roots that we are going to get. They are exactly that number, and they are distinct. Those are the 3 steps there. So let's look at step 1 and see if we are able to do another step depending with our time. So let K be an element of this set, right? Then WK to the power n is going to be equal to R to the 1 over n. So remember the formula that we have, the nth root, so you can rewrite that as R to the 1 over n. And then we've got E to the theta plus 2 pi k over n I, right, as our argument there, and then we are saying all of that to the power n. We want to see if we can get z in the end, and this is simply equal to, if we write it in the other polar form, then we can say this is going to be equal to R to the 1 over n cos theta plus 2 pi k over n, like that, plus sine theta plus 2 pi k over n, and then we've got an I there, and then we've got our brackets to the power n. And then we've got a theorem that tells us that if this happens, if you've got this complex number in this polar form to the power something, then what you do is you say R, you're going to put the power for R, right? Obviously, there should be brackets here, I think. Yes, there should be brackets there, right? And then inside the angle, what you're going to do is you're going to multiply by the power, and so you end up with theta plus 2 pi k over n times n inside there, plus sine the same theta plus 2 pi k over n times n, and that is your angle I, like that. And I'm not sure what the theorem here is, and I'm sure you can you know the theorem, so you can add it here. If you know it, you can post it in the chat and then I'll write it here, but otherwise I think if you look in the textbook, you know what the theorem is, right? And then from here we then say, if I have got this, I just multiply, so 1 over n times n, I get 1, so R to the power 1, and then I've got cos, if I multiply by n there, I get theta plus 2 pi k, and then plus sine theta plus 2 pi k, and I there, and then we have that. And this is so I thought someone would post the theorem. Okay, let me just tell you what it is. It is what we started off with. It is De Moivre's theorem, so you can put it there. So that's the theorem that we used there. And then once we have this, then we can say, well, if this is the case, then we know that this is going to be equal to r times cos theta plus sine theta I. And what is the reason? The reason is this complex number is equal to this, and this is by the theorem that we just stated, right? I think that's theorem 6.5.3, right? It told us that if theta is going to be, if theta 1 is equal to theta 2 plus 2 pi k, then the complex numbers have to be the same, right? So we can say this, and then we've got this. If we rewrite it in the other polar form, the shorthand one, we can say this is equal to that, and that is equal to z as required. And so therefore, we have shown that if you've got wk, it is an nth root of z, because we started off with wk to the power n and we ended up with our z. And I hope the explanations were sufficient to understand what's happening there. And we are going to stop here. So tomorrow we will do step 2, and then you will do the other step as an exercise. So that is all for today, and then tomorrow we'll do some examples of how to find nth roots of a complex number and draw them on an argand diagram, or sorry, argand plane or complex plane. So that is all. Thank you. Enjoy the rest of your day. If you have questions, you may remain behind. I'll be here for a minute or so to answer any questions. Otherwise, have a lovely day and a lovely week ahead of you. Thank you. Okay, it seems that there are no questions, so thank you. Enjoy the rest of your day. Bye.